Hey guys, some sad news before we get into today's podcast. So, as you guys know, Parker and I, we're now living together. So, podcast got a huge upgrade, new setup, and everything. And with that, we're also, experimenting with new stuff. So, we tried out a new camera for this episode, and it did not exactly work out the way we wanted it to. So, we kind of got left without a video. So for this particular episode, we're gonna go back to the original days, the videoless, faceless YouTube videos. So don't worry, back to normal in the next episode. But for this one, enjoy.
It's the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we welcome you back to episode number 79, where today we are going to be talking about waves.
Waves.
What waves?
Waves are everywhere. No, waves are literally everywhere. As we've learned recently in modern physics, that everything is pretty much just a wave. And so there's a lot to talk about here. More than just, matter waves of, what I mean, like quantum mechanics. There are like classical types of waves that we're going to talk about. And they're all super, super interesting.
Just different types of waves, different properties of waves, just episode about waves, because, you're right. Everything is waving around us if you think about it. And especially with the whole particle duality thing, at the end of the day, you can think of everything as a wave. So It definitely helps a little bit.
And we're definitely going to get into the wave function, which, I'm currently taking the third year quantum mechanics.
So that's the actual quantum mechanics one.
Yeah, it's the actual. Yeah. What we took last year was intro.
I think in every university, second year quantum mechanics starts introduction. There's not a single second year quantum mechanics 100%. Course. It's all intro, and then third and fourth is obviously when you specialize.
Quantum mechanics 1 is what it's called.
That's cool, man. No, I'm very excited. That's definitely gonna be a cool.
You're
course.
Gonna take it.
I'm gonna take it next year, so I'm very excited as well. But anyways, let's not talk about that. But we are gonna be getting into that in today's episode, just a little bit, maybe. Obviously, focusing more on the wave stuff, but getting into all of it equally.
Before this episode starts, as we do every single week, we have a little bit of news for you guys, a little bit of comment of the week. And after that, we will get right into the episode. So, to everybody who's listening right now, it's not really a milestone, but like 14.5 thousand followers on Spotify. Thank you very much, everybody.
We're almost at 15. We're at 20 total right now, right?
No. Almost.
We're almost at 20 total. Counting YouTube and everything?
No.
Still
not yet.
20.
Not
okay.
yet. Not yet.
Close. 20 will be still a very, very crazy milestone.
For sure.
For followers, it's definitely nice. So thank you for everyone who continues to follow. If you are listening to this on Spotify, go give us a follow. There's no like on Spotify, right?
No, there's not. No. But also follow us everywhere else if you're listening to this. Google, Apple. I don't even know where else. I know we're on a bunch of platforms. Yeah.
So whichever platform you're listening to this on, why not just give it a follow? And if you're on YouTube, or if you're not on YouTube, come on YouTube. Go give this a quick look, because
bada bing, bada boom.
The videos are always something that we like. So moving on to the comment of the week.
Actually, one second.
Oh, we forgot all of the news. The news wasn't even
done.
I got very excited there for you guys. I'm sorry.
In terms of downloads, we're actually every single month there was 1 month that was a little bit off, but every single month since we started, we have been getting more and more downloads every month, and so now, we're just hoping to keep that trend going. And this month last month we were at like 32,000 in the month, which is more than 1,000 downloads a day. So that's pretty cool.
And that was last month. And that was last month too.
Yeah. So total downloads, we're at 232,000 downloads.
Almost at a quarter million. We're so close. We're so close. Oh my, that's gonna be a very, very, very crazy milestone. Again, thank you for everyone that continues to download our episodes everywhere.
All we do is we just sit here in our living room and talk, and you guys listen. So thank you, everybody.
Thank you, everybody. Now I think we can go onto the comment of the week. Now, we did actually have quite a few comments this week, which I always appreciate. And they were all wonderful, but I just had to do one from the emails. It just had to be the email. So listen to this comment real quick. Now, I cannot properly pronounce that name. It's probably Stazek, if anything.
I don't know.
But someone sent us an email. Stazek, if you are listening, let me know if this is the correct pronunciation. And he's basically a 15-year-old that started to listen to our podcast on Spotify. And he's basically just saying that he's on this episode and he just wants to say that we're doing a great job. And he's just talking about that he's really interested in physics, especially connected with astronomy, and finds our podcast really interesting. And maybe someday I'll go to U of T too. Inspired by us, hopefully. I think that was his intention. So thank you so much to Zach for that wonderful comment. I mean, 15, that is...
very young.
Like, that is beautiful. Like, that's wonderful. I mean, I didn't know what a podcast was until 2 years ago. So the fact that a 15-year-old
is even more surprising.
Okay, yeah, I wasn't really anyways, but the 15-year-old being so interested in math and physics, taking this clearly, I mean, an hour a week of your time, especially at 15, just to take it out to listen to a podcast is not normal. Especially one about physics.
I feel like you have time when you're 15.
Yeah, but who listens to it like if you're listening to a science podcast, you really have that passion. So Stazek, thank you so much for that email. Wonderful passion on your side too. And we're going to continue doing what we love to do.
Awesome. All right. Boom.
Let's get into
Let's get into waves. I think the first thing that we can talk about is, what is a wave? Well, the first thing that I think about is a sine wave.
When
I think about waves in general, because a sine wave, or like, we're not gonna get into like superpositions of waves. Like, if you just think about like a simple wave that has a wavelength and a period and all that stuff, a sine wave can describe any kind of wave. If
in essence,
there are more complicated waves, but those are just, you're just adding sine waves on top of sine waves to make those more complicated waves. But if we're talking about like waves in the water, sine wave, all that.
All of them can be, yeah. I mean, because now what we're basically talking about is extrapolating the mathematics behind what we have as the physics. Or not the physics, but like the real world. So we're seeing something, and especially with physics, we have this handy thing called, or not called, but basically just equations of motion. And with all waves, there's an associated wave equation. And this is simply a fundamental property of any wave. And if it's a sine wave, it's literally just sine x, right? Because that's the wave. So the whole point of this is using the mathematics behind all, behind sine, behind trigonometry. We can apply these to the real world and extrapolate data about them through these waves. So what you were talking about a second ago is something that we also did speak about in a history of physics episode, a Fourier transform, or like a Fourier.
Not transform.
Well, not a
Fourier
transform.
series.
Fourier series is basically what you described by adding up the different separate sine waves, because cosine waves are basically sine waves. So you're basically just adding multiple sine waves, and you just get a very complicated wave. You can shift some of them and you can get something else.
Did you know I recently actually really understood for the first time what a Fourier transform was?
Because of quantum mechanics.
And it's not because, well, technically I should have. There were notes that I didn't read them though. But no, I'm talking about maybe during the summer. I looked up Fourier transforms and I actually understood what it was. Very interesting. If you're in or let's say going into university math, maybe let's not say first year, that's a little bit too complicated, but if you like to look ahead, I definitely recommend looking at Fourier series and then Fourier transforms. Very interesting.
Very interesting. No, I mean, Fourier, and they are, again, the building blocks to how we get our waves. Because if you think about it, now waves can be so many things. Like, we think about them as light waves, sound waves, but there are so many different types of just waves when you're talking about it in general. We just have said, okay, like these commonalities are what we see. So even when we extrapolate this using Fourier series and stuff like that to make a more complicated wave, all that's really doing is just, again, getting us a better understanding of the properties of that wave. How does this wave move? Number one, with position. Number two, with time. That will be your two-dimensional wave, right? So there are a lot of advantages to using all of these extra principles just to get a better understanding of our wave, right? And every wave, just fundamentally speaking, a physical wave at least that we see in nature, all of them have two separate fields. All of them have two separate fields that is basically oscillating back and forth. Now, the whole thing about a wave, like, why is it really called a wave, is because the idea is that, well, it's waving back and forth from a point of, an equilibrium point, right? So there's some middle ground, and the wave, or would just oscillate back and forth between them.
But what do you mean by two mediums, like you said?
Everything requires two mediums. Now, the fundamental light will require electro and magnetism, right?
Okay.
And they require two fields to propagate. The same way with sound, it requires strain and stress, which are two different properties of the air that basically allow sound to propagate through it. And all other physical waves that we see in, nature, anything real, again, mathematical is obviously different. I'm saying anything physical that we can actually see in the real world, sound, light, obviously the biggest ones, you can assign these fields to it. So in more complicated and more advanced, mathematics and field equations and physics, we can actually maybe deduce these fields, part of all of these equations, and actually understand not only how the space around it is moving, but how the individual fields are moving.
Oh,
right. And that's an advantage of this relationship between these two fields that have to be present for a physical wave to occur. Right. And because both of them are basically pushing back and forth, is how the wave is able to propagate. And this is through with electromagnetism and also through sound. Right.
But I don't actually know if this 100, for 100% certainty.
Let's say.
I'm saying the electromagnetic fields that oscillate, they don't push and pull each other. You know what I mean?
They're perpendicular.
They're oscillating perpendicularly.
They're
Exactly.
perpendicular, but they require. What I'm trying to say is, for the wave to exist, there is a requirement of two fields. Is what a requirement is for a wave to exist.
All right.
Right, and these two fields basically or allow it to propagate through space-time, right? In any situation, in sound waves, we can talk about, it would still be space-time, but you know what I mean? It would be probably air and stuff, because that requires a medium to propagate. Maybe we can now get into a little bit of, I don't know if this is a little too base, maybe we can get into a little bit of just sound in general, because I know sound is it's the most common wave. When you think of a wave, again, when you hear wave, a big thing that you think about is sound waves.
Sound waves. So when you hear a sound wave, think about how insane. We were talking about this the other day, about how crazy sound waves were. So essentially, you're hearing a noise, and to your brain, that's just you hear a noise and you're like, okay, whatever. But what's actually happening? Let's think about this. Your eardrum is vibrating back and forth, and what's making it vibrate? Well, it's the sound wave. Well, what is the sound wave? So a sound wave is just through the air molecules are going back and forth, because the source of the sound creates high pressure and low pressure areas in the air. Yeah. And so the high pressure and low pressure areas is what pushes back and forth the air molecules, and that propagates through the air and then reaches your eardrum. And your eardrum literally vibrates to the tune of the high and low pressure. I'm making a movement with my hand if you're listening on Spotify or whatever. But your eardrums are going back and forth at the same exact rate that the air is vibrating. And your brain, in turn, translates that into a noise. Now, it is a lot more intricate than just that, because you wanted to talk about like what makes a sound different.
Yeah, that in a second. But I wanted to continue on your whole discussion about how it vibrates and then your ear vibrates at that. And that is, in the essence of it, the fundamental reason why sound exists, and that's vibrations, right? So everything in the world vibrates. We are vibrating right now. We're giving off infrared radiation that would not be sound. But
very true.
Everything in the world has a natural frequency. This is your lowest resonant frequency, and we can maybe get into it in a second. But everything has a natural frequency, the frequency at which it vibrates. Now, if you happen to disturb this body, now when I say disturb, it's like you can hit it, you can pluck it for a string. Very many things. I'm just thinking about, well, and anything if you're just hitting something, right? That's the easiest way to think about it. If you disturb it, what's actually happening is, for a sound to occur, you're first hitting it at that lowest resonant frequency. So you're vibrating it at the speed that it itself vibrates, and it creates a sound. Because what's again happening is lower vibrations would not register in your ear, but higher vibrations would basically cause the molecules in whatever you're hitting again to vibrate with that same sound. So the moment you hit it, the vibration in the air around it is actually what's causing the sound. Because when something is stationary, again, no sound is being created. But when it's hit or something like that, there are pressure columns, as you were talking about, in air that get sucked in and sucked out. This is compression and rarefaction columns. Yep. So compression columns are dense air columns. Rarefaction columns are less dense air columns. And this less dense, more dense, because these molecules from the item itself are vibrating, it vibrates this pressure. This pressure is now moving back and forth at the same speed of the vibration.
But here's why, though. If you think about it, imagine you have, like, this is just like pressure in general. If you have a high pressure area, like let's say the inside of a balloon, and then you let go, or you open a hole, the high pressure air is going to move towards the low pressure air. So what actually makes the sound travel through the air is that, okay, you have a high pressure, low pressure, high pressure, low pressure, and the air is constantly moving from high pressure to low pressure. But as the air moves, it leaves behind a low pressure area. And so it moves back and then forth and back and forth. And that's what creates the vibration. And then, of course, the air molecules are touching each other. And so if one moves, or if like one column moves, then it pushes the rest of it. And that's what causes sound to just go across the air.
And that is why when you just hold, for example, a string, and you just hit it, and even if you hold it tight and you just hit it, probably you won't hear anything loud. Do the same thing on a guitar. It's a whole sound. And again, the reason this is happening is simply because more things are vibrating. So there's that whole, what's it called? I don't know what it's called, but like like the wooden part of the acoustic guitar. You know
The
what
body.
I guess, yeah, the body of the guitar. So the moment the string is plucked, I'm just thinking of a guitar as an easy example. When you have a string, just nothing there with it, just air around it, and you pluck it, the air around it, there's just a little bit of that that's vibrating, that then gives you a little bit of sound. Maybe you hear that tick, tick, you know what I mean, when you stretch a string and you try to hit it. But then in a guitar, the same vibrations is now sent through the whole body of the guitar. So this is actually also a thing of resonance. This is where resonance comes from. What happens is the body of the guitar vibrates at the frequency of the string. Wherever you are playing the particular string, the body is now vibrating at that frequency. And because the whole body with the air around it is now vibrating at that frequency, you hear it a lot louder. It amplifies is the easiest way to think about it, because literally what happens in the wave is the amplitude increases. Nothing else changes, obviously, because the pitch and everything is the same, but the amplitude increases. So they're all, and it's the same thing even with like a tuning fork, and you put it in like a box, and it just all of a sudden, whoa, you just hear this crazy loud noise. It's all again about how many things are vibrating and how these vibrations are sent through to other objects. A simple or another example of this would be, and this is quite common, when you I don't know, is this a common physics experiment? When like you have like I'm just gonna say it, like the two tuning forks, for example, or something like that, like two things together, and you ring one of them, and then after a second you stop ringing one of them and the other one starts ringing, and that's basically resonance for you.
Well, it's not that it starts ringing; it's that causes.
No, that's what I'm trying to say, right? Okay. So that was the point that I was trying to make. So what's actually happening is, because they both have the same natural frequency, because they're the same object. When one starts vibrating and making a sound, so does the other, because they have the same natural frequency, and they start hitting, and that one starts vibrating too, and boom, it's magic. But no, it's just physics.
And now is a beautiful time to actually mention or introduce frequency and wavelength. Okay,
properties of a wave. So it's a good time.
As the object is vibrating back and forth, the amount of times that it vibrates back and forth in 1 second is the frequency. And that actually comes in units of hertz, 1/seconds. Okay, so everybody's heard of hertz before, this note is 20,000 hertz or whatever.
Ooh, that's high.
That's very high.
That's literally the limit of human hearing.
That is the limit.
Relax. Yeah,
but now you know what that means. When you hear something that has a certain amount of hertz, it's because it's literally moving back and forth, and it's causing your eardrum to move at that same frequency at 20,000 times per second. Okay. Now imagine this. Okay, I make a noise, and it produces these high and low pressure columns that are moving at the speed of sound, which is 344. I thought it was 344.
Something like that. Something like that.
The thing about sound is that the speed of sound actually changes based on the medium. Okay, so it's different in water or metal. It still works in metal, but we're not going to get into that right now. What I'm trying to say is that the speed of sound in air is relatively constant. Let's say, does it? It changes with temperature, right?
Of course.
Yeah. Anyways, we're gonna pretend like it's constant for now, because we're in ideal conditions. And now, let's say I produce a noise, and we take a snapshot in time of the high and low pressure columns. Okay, based on the frequency, you can deduce, like how many of those columns would be in between Ray and I. Now, what would happen if Rayhan's ear is moving towards the noise that I'm making? Well, his eardrum would literally be experiencing those columns faster than they were moving towards him if he were to be still, right? Like, imagine there's a bunch of waves on the ocean. You could either be standing still in the waves, or if you're on a jet ski, you're going to be experiencing those waves at a faster rate. Now, what does that translate to when we talk about sound? Well, I just mentioned 2 seconds ago that the rate at which something is vibrating is the frequency, right? And lower frequency is lower pitch noises, and higher frequency, higher pitch noises, okay? Now, I am producing a noise. Rayhan's eardrum is coming towards that noise. And so it's the jet ski going through the waves, experiencing them faster. All of a sudden, his ear is experiencing a faster frequency than what was originally exiting my mouth. Now, what does he hear? He hears a higher pitch noise. Now, think about this. When you're on the side of the road and an ambulance is coming your way, that ambulance is the speed of the ambulance is adding to the speed of the sound that is coming your way. So the waves are getting pushed closer together, and when they hit your ear, they sound like they're going faster than they actually are. Now, when the ambulance passes by, it is moving away from you. The source, or I guess it's all relative.
It
is a source. But it doesn't matter. The ambulance could be standing still, and I could be
that's
going
what
the
you
other
mean.
way.
Yes, of course.
It doesn't
Yes,
matter.
If the ambulance is moving away from you, or you are moving away from it, is what you're
the only
trying to say.
thing that matters is that there's separation happening.
Yeah.
Right now, all of a sudden, I'm going the other way, and now my ear is hearing the noise, but at a slower pace, and what you hear is. Right?
Yeah,
it goes high and then low. That's what you're hearing.
Yeah. And that is the Doppler effect.
That is the Doppler effect.
That is the Doppler effect. So probably by a guy named, it is obviously.
No, 100%.
I just forgot the guy's first name. But obviously crazy. But what it actually shows is that nothing fundamental is actually changing about the wave, except for the one fact, except basically for frequency. So the speed is staying the same, which is interesting, which is a very nice thing that you brought up, but the frequency is changing. Also tells us something about the relationship between the frequency and the speed. Like how is somehow the frequency or the pitch getting louder, but the speed somehow not increasing or decreasing? Well, that's simply the equation of speed. Right? That's simply how frequency, speed, and a property of wavelength are all related to each other. And it's quite intuitive to see that if you were to increase the frequency, as in, I'm just thinking of someone who hasn't heard of frequency before. Like if you draw one whole wave in a certain interval, now draw 3. That's increasing the frequency. It's just intuitive that the spaces between the waves get smaller too. It's just intuitive, right? You can almost see it in your head. So when one goes up, the other comes down to keep that constant.
Yeah. And also, quick fun fact, when you see like an airplane going faster than the speed of sound and you have the sonic boom, that's literally because the airplane is creating a noise, a loud noise. It's vibrating the air around it, and it's creating these high and low pressure columns everywhere around it. But what happens is that the faster the airplane travels, the closer together he's squishing those columns, right? As we just talked about the Doppler effect. But what happens when the columns get squished so close together that it's infinite, that it's pretty much like it reverses, you know what I mean? Like the noise gets produced after the event happens. There is a barrier there, right? Of course, because you go from sending waves forward to compressing them and then sending waves backwards. And that is where the boom happens, because you have to literally squish those high and low pressure waves to essentially zero.
Yeah, I mean, you're basically causing like instantaneous thunder at all seconds because thunder, I mean, I don't know where, okay, this just came into my head, but thunder is literally just a rip of pressure regions. Like what actually happens is in in the clouds, especially when it's about to rain, when it's about to go crazy, there are regions in the sky that have severe high pressure and severe low pressure, which basically causes the clap that we hear. It obviously starts with the lightning, which then causes the thunder, but I mean that's another story. But at the end of the day, what's actually happening is this high and low pressure is there's simply a difference between that. So when you're reaching these speeds, remember, as you were just saying, the air around you is also traveling at the speed that you are, or is vibrating at the speed that you are. So when an airplane is flying through the sky at, subsonic speeds, the air around it is still traveling at those speeds. Now push it to supersonic, the moment like you touch Mach 1, right? You have the air around you literally traveling at the speed of sound. So we have sound being made, as you mentioned, by the aircraft itself. But the sound is not fast enough to leave the aircraft because the aircraft is now faster than the sound, which is why it's always an intense loudness heard everywhere else. And actually, I mean, this is a famous thing. I think we've spoken about the Concorde before.
We've never spoken about
the Concorde before? Well, the Concorde, definitely search it up if you haven't heard of the name. The Concorde was a very, very famous, very expensive flight that traveled supersonic speeds. I believe it went to Mach 2, actually.
I don't know.
And it went pretty fast.
It was too loud.
Yeah, that was
it was way too loud.
The problem is when it was close to residential areas, you have to understand that even though it is trying to maybe slow down, even when you're Mach 1 or anything higher, remember the air is, again, if you're hearing something, that means the vibrations from there have reached you. So in the same way, if you're hearing the boom, so are your windows.
Wait,
and your house. So what I'm trying to say is the problem with the Concorde for a very long amount of time is that when it actually used to come in some residential places, is to just break windows.
Yeah, the windows would break.
And again, windows break. Why would they break? When you surpass that natural frequency. When it can no longer vibrate without breaking the structural integrity that we call glass. Because glass is an amorphous solid, so it's a really weird solid the way it's made anyways. So when it vibrates at this or higher than the specific frequency, that's why opera singers can. So it's not like for an opera singer to break a glass, I don't think it's a crazy thing because a lot of them should be able to do it. Because the whole point is you can be able to control your pitch. So if you exceed a certain pitch, should just...
The reason why it's impressive is because you have to increase the intensity.
Intensity as well, of course. The amplitude is what is actually more important. You're very right in that. The amplitude of that wave is actually very important.
The frequency has to be exact.
Yes, of course.
But I think the hard part is actually...
The amplitude has to be it has to be exact or higher, but the amplitude has to also be great because it actually has to literally knock it out.
It can't be higher. It has to be the exact same frequency.
Oh, because then it'll vibrate and break. Exactly. Yeah, you're right.
Yeah. If it's a different frequency, it won't
You're right.
be...
No, you're right. You're right. Because then it'll vibrate at resonant frequency, which will then just cause it to break. And, well, I mean, interestingly enough, a similar thing with glass that I just thought of right now is that water thing. It's a little different.
Yeah.
You know, when you take water and you rub it around a glass and you hear that... Like that beautiful... Okay, that was not beautiful, I know. But you know what I mean. I mean, if someone's done it at home, maybe.
Yeah.
But again, that is... Okay, that's a little different, though. That's actually a little different. It's happening because of a little different process.
Isn't it the friction making your finger?
Exactly.
Yeah,
so it's basically the water... So it's basically the friction between the... It's called a slick and... No. It's called a stick and slip. Or the slip and stick. Something like that. Which is basically the type of wave or the type of sound created. And the way that it's caused is basically because of the water between your finger and the glass. That, when you get the right thing, that starts to vibrate at the glass's natural frequency, which then makes the top of the glass vibrate at that frequency, which then causes a sound.
That's cool.
So it's really cool. And I mean, anyone can do this at home. You just dip your finger in water and try to go around the glass at a certain pace. You'll find the pace, and when you do, you need enough water.
It has to be a wine glass.
Well, wine glasses would definitely work better. I don't know if it has to be. It's just better because I'm assuming it's a lot thinner.
I've never done it.
It's a lot
anything
thinner,
else.
so I'm assuming maybe it's a little bit easier to get that frequency going. I could be a little incorrect in that, but at least for how to do it, I mean, it's a really fun thing that anyone can do, and it always teaches you just a little bit about, you know, how all this stuff works.
I wanted to say earlier when we were talking about the Concorde, like imagine doing like half a kilometer per second. Like that's very fast.
I mean, it did more. It went to
More
Mach
than
2. It went to like over.
Really?
Over. Yeah.
Wow.
I'm like, okay, I mean, I don't want to bank myself on this because, again, on the spot, I haven't actually done this, but I believe it reached Mach 2. I believe it was very fast. It was a very, very fast plane.
Because how fast? I feel like airplanes travel at like 400 kilometers per hour?
700.
700?
700, yeah.
Really?
Yeah.
Okay.
I remember this because I was in a plane one time going to, this is a funny story. I was going to the washroom. I don't even know how I remember this. I was going to the washroom, and then this one plane. When have you ever seen this? The speed. I've never seen the.
Where?
I maybe it's common now, but like this was a very long time ago on one plane, and I saw like on this huge screen, it was the speed of the plane, and that was 700, and I can never forget that sight.
No, I think
And it's
nowadays
somewhere around 600-700.
Nowadays, like they say on the screen, like in the. Like
I think now you can see on
yeah.
all of the navigation
Yeah, yeah.
screens, but believe me, this was a time when, well, you couldn't do that.
Oh my God!
Mach 2.04.
That's 2,200 kilometers per hour. You could go.
That's like
from,
3 times the speed of today's planes.
That's. Listen, you can go New York to London
Before it's you can arrive at London before you left New York. If you do the time, because if you account for the time, like that's how it works. Like it's so fast. It's pretty crazy.
Doesn't that happen anyways?
No,
Wait,
not with
no.
a regular plane. No, because it would take.
Oh.
Yeah, no. But anyways, I mean, we're definitely getting straight, very off topic. But
Wait,
planes
no.
is a good.
That would be going the other way.
I think it's going the other way. Wait, I think I
London
messed it
to
up
New
too.
York.
I think it's
yeah.
London to New York before London.
Yeah, because it's earlier in New York.
I think that's what we
or
meant.
whatever.
Yeah, I think that's what we meant. But with planes right now, we are at peak efficiency. We can't go any better than this.
The Concorde brings you back in time.
No, I mean that would be okay. Anyways, it's a very cool thing. Sonic boom definitely got us really straight off topic, but sonic booms are, I mean, still a fundamental thing of waves. And again, all the reason is simply because of the vibration. And we've been talking a lot about sound waves so far. And I mean, we can't continue for sure. But a fundamental thing that you mentioned that may have gone under the radar for some people is the fact that sound needs a medium to propagate. Because you said sound needs air, sound needs water, sound needs something. Because again, what's actually happening is at the end of the day, as we're saying, these are all vibrations. It is vibrating. Things are vibrating. Now, this is a type of wave called the longitudinal wave. Now, there are 2 types of waves. The other one is transverse, but we're going to talk about this one for a sec. Longitudinal waves are where the molecules, particles, items, objects, whatever is propagating, is traveling parallel to the mode of propagation. So in this case, we have sound. So if I am talking to Parker and my voice is going this way, the molecules are also vibrating in the same direction. And those are longitudinal waves. And the whole premise of sound is that it requires a medium to propagate. And that is why, and if you say, if you see like the scream in space thing, because at the end of the day, no one would be able to hear you because sound simply cannot travel. It wouldn't have a medium to travel because there are no molecules. So that's another story. But what I'm trying to say is there's no vibrations happening between you and the other entity to actually get the sound across. Light, on the other hand, is a transverse wave, right?
Oh,
that's a little opposite. So
yeah.
This is where your fields are actually traveling perpendicular to the mode of propagation. To the mode of propagation. So if one is moving, well, again, if you're not seeing the video, then you're probably not seeing my gestures here. But you can probably think about this. If the mode is going in a direction, just think about something perpendicular to it. And well, I don't think that was not required at all. That was not required at all. You guys can picture a perpendicular thing. Anyways, the point being, light doesn't actually need anything to vibrate. Interestingly enough, there was a big experiment for a long... Again, shit, I just noticed this. We do this so often. But the experiment for the ether, with the Michelson-Morley experiment that actually semi-discovered interferometers, basically started with the premise that, or thought, the hypothesis that there was an ether that allowed light to propagate, because everyone was so used to the fact that waves needed things to propagate that we're like, okay, light does too. So Michelson and Morley set out to prove themselves right in a way that they said, hey, there's this propagating material everywhere in the universe called the ether, and light is simply traveling through it. Anyways, they did an experiment and it failed. So it basically proved that, hey, there isn't a medium that light requires to prove. And how did they do experiment? Really quick, they basically just tested the speed at which the light traveled in perpendicular directions, right? So if there was an ether, then it would not be traveling at the same speed in perpendicular directions. So that tells you something about it. And anyways, continuing, it just gives a little more emphasis to, where this whole situation is, the difference between sound and light, how they require to propagate, and just really what makes them up.
All right, I have something crazy.
Let's hear it.
Okay, so light.
Light.
We mentioned the Doppler effect earlier. The same kind of thing happens, but it's very different. In that the speed of light is constant in all frames, which is very easy to say and kind of hard to wrap your head around. It takes a minute.
Now I fully get it.
No, now I get it.
I almost fully get it, but it takes a minute.
When you hear it for the first time, it doesn't really make sense, and you don't really understand the consequences of that right away. But essentially, here's one of the consequences. We did mention this before. If you move towards a light source, the speed of the light won't change. The only thing that actually changes is the wavelength. The wavelength gets shorter. And so your eyes get to see something or a photon that has higher energy.
This is also the Doppler effect, by the way.
It is the Doppler effect.
Doppler effect is just with waves in general. Like, it's nothing to do with sound waves.
No, it's definitely different. Like, it's not...
It's literally the same thing. It's the exact same formula. It's like the same thing.
Are you sure?
Yes. Because waves are waves, man.
I guess.
Waves are waves.
Okay.
Like, if they have a frequency, if they have a wavelength, they're waves.
Sure. So, boom. Doppler effect works the same way with light. Here's the crazy thing, okay? Back in the day, imagine, I've definitely said this before, but imagine being in the 1600s and, it's a life or death situation. Somebody says, measure the speed of light or you're dead. What do you do? What do you do?
Jesus, bro. That's an ultimatum.
What do you do? Like, think about it. You don't even have a computer. You don't even have a camera. What do you even do? Well, I don't know what year this was done in, but it's definitely an insane experiment.
I don't even know. Yeah, go ahead. I want to hear this.
Okay. And this was definitely, like, recent, but it was, like, this is just... The reason I said, like, in the 1600s was just to put you in that space of, like...
No, but wait, didn't Einstein do it for the first time? Like, calculate the rough number?
Yeah, but I'm saying there was an experiment. I don't know if you know it. I don't know if we talked about it in the astronomy episode, but listen, okay. So, somebody said, okay, the Earth and Jupiter have, separate orbits. And at some point during the year, or, whenever it coincides with the orbit of Jupiter, the Earth is going to be moving towards Jupiter. And at a different point, when the Earth has time to rotate past Jupiter, it'll be moving away from Jupiter. And so, wait, am I thinking of this wrong?
No, you're actually thinking of it exactly right.
Okay.
No, you're right. Yeah.
Okay.
No, the way they did it, again, I haven't read up on this particular experiment, but I know it does have things to do with the Earth's orbit, Jupiter, and measuring the time that it takes to revolve. I know those properties are involved, and this was in fact done in the 1600s, 1700s.
Oh my God, no way.
This was way before Einstein, actually.
Wait, I think...
Are you mixing up like two experiments?
No,
right
I
now,
think
yeah?
I am, because no, we definitely had a problem set where like Jupiter's moon, where
Wait,
it goes
I
around.
remember
Yeah,
something like that.
yeah. Like there's Jupiter's moon, and then when the Earth was going towards Jupiter, like the what's it called? Like, you know, when a...
No, I know what you mean. No, I know what you mean.
I can't think of the word.
Can't say the word. No, but I know what you mean though. But we did do a problem like that actually. But I don't know. I mean, that doesn't have anything to. I mean, it's not directly to do with this, but that is how I believe it was something like that done. Because I mean, if you think about it, at that time, you have to understand that people were... light is either two things. Light is either infinite speed or it's just too fast to measure for us, which is what we were under the impression of.
Yeah.
For like the longest amount of time, right?
I have to search this up. But
I'm
keep going.
No, I mean, I'm just trying to think about finding the equation, or not finding the equation, but finding even the rough speed of light in the day where literally nothing was even thought about, or you're not even thinking about frames of references. You're not thinking about what the requirements are or anything like that.
Okay, I found the experiment and I was actually right.
Yeah, Romer's did. Okay, cool.
Okay, so what he did is he timed the eclipses of Io, Jupiter's moon.
Yeah.
So he estimated that the light would take 22 minutes to travel the distance equal to the diameter of Earth's orbit around the sun. And this would give light the velocity of around 220,000 kilometers per second, which is
relatively close. Which is very, very, very
not
close.
bad. One sec, I need more details on this. I need more details because I remember we did this. I'm pretty sure.
I don't think.
No, we didn't do it.
Yeah, but I know what you mean. We did a very similar question where we were talking about Jupiter and its transit time, and basically trying to simply find the time it takes for some kind of signal or something like that we were doing in our year. But again, I mean, it's really impressive that these individuals even tried to find something like this.
This is what happened. I remember. So when the Earth is moving towards Jupiter, the time that the moon was eclipsed, it took less time for the moon to eclipse. Wait, is it the moon that eclipses? Yeah. Because the moon. Yeah. This is definitely.
This is such a funny episode, man. God
because this is actually like an insane experiment.
Yeah.
If you think about it,
1600s, you discover the speed of light.
No,
like what?
Seriously. So basically, when the Earth was going towards Jupiter, it took longer for the moon to go across than when the Earth was moving away. And so what he did is he calculated the difference between the times, and
he just did some crazy math.
Wait,
what? That's crazy. That's pretty next level. Okay, that's very impressive. Again, a lot of this was probably starting like with trigonometry. Like if you think about it, a lot of it was probably starting simply with triangles and different geometric shapes, just trying to understand the angles between all these things. And then I'm assuming estimating the speed from there. Because what I'm assuming is all of this was compared to Earth's orbit or something like that. Like it was compared to something that we were already relatively sure of. And then we got this approximate speed of light. Because again, I mean, 220 relative to 299, which is the actual speed, is very, very, very close, especially in the 1700s.
I mean, like, in terms of, like, producing an answer.
Yeah, I mean.
Very, like, who
who even thinks about it? Like, you're not, like, you light, I mean, the 1600s, like, you light fire. You're not really, I mean, I don't even understand the thought process that goes into thinking, hey, what speed does this travel at?
Okay.
Crazy moment?
No, okay. What I said was right, but here's what actually goes down, okay?
Let's hear it.
So they knew, like at that time, it was like Galileo's time. He was going off with astronomy and all that stuff and his new telescopes and all that stuff.
Mm.
So they figured out the timings of the eclipses of Io. So they knew when it should happen.
Okay.
Okay?
Okay.
So what happened was that when the Earth was moving towards Jupiter, the eclipse happened, it says, about 9 minutes early. And when the Earth was moving away, the eclipse happened 9 minutes late. So they knew that they knew the time difference between what actually should have happened, and so they were able to calculate it from there. That's just like trigonometry from there. Or something
Yeah,
like
if you
that.
know the distances, I'm assuming they knew some kind of distances between these planets, or at least had estimations.
You know the distance, and you know the difference between when it should have came and when it didn't, and when it did come. And anyways,
Man, that's super cool.
No, that isn't. Imagine using
my.
imagine using Jupiter and the timing of the eclipses and the knowledge that the Earth has some kind of orbit and Jupiter has a different kind of orbit, and they have a relative distance between each other to calculate the speed of light. That's some next level stuff. Like, seriously.
Man, like, to even think of something like that.
No,
though.
I know. Like, how? Like, how?
Jeez.
Wow.
No, I mean, they're just
I'm blown away.
They're just some people, you know. I mean, they just clearly just think differently, man.
No, they understand.
This was Huygens,
something.
right? Like, Huygens was a part of it, was he not?
No, I don't think so. Actually, let's. No.
Kristen Huygens,
It was
right
the
there.
same period.
Oh, same
but-
period as Kristen Huygens.
Yeah.
Well,
Different
places.
places.
Different places. Oh, different numbers, I'm assuming, too. That's, wow. That's definitely an impressive experiment that he performed there. Again, just showing you a little bit more about the fact that, hey, nothing is infinite. Nothing is infinite. Now, the interesting thing about light, as you were talking about, you know, with the whole reference frame thing, is Einstein basically, again, don't know the exactness of this particular story, but the idea was that, hey, there's this speed at which nothing can travel faster. So the whole basis of special relativity was written. I don't know why I'm talking about this, but I just thought about Einstein and Light. But the whole basis of special relativity is basically the fact that light is constant wherever and however you're looking at it. So if you ever get faster, light's not getting slower with respect to you. Time is simply changing, and that's the way he did it in this case. And it's the way that we think about the universe, and we believe the universe works, right? Having this one speed that basically trumps all. And again, with this speed, coming back a little bit to the Doppler effect again, the fact that the speed is always remaining the same. Right. And with light, it is, even though it is called a Doppler effect, it's a little bit different. So when anything is moving away from you with light, with respect to light, you call that a redshift. And when anything is ever moving close to you, you call that a blue shift. And obviously, most notably, you don't really see this ever in daily world because, you don't really have those speeds, those distances or the frequencies. But when we're talking about galaxies, for example, the whole premise of the Big Bang literally started when Hubble noticed that. It wasn't Hubble that started it, but it became big during that time when they noticed that a lot of these galaxies are red and they're actually moving away from us. So if they're moving away from us, and then you can just backtrack it in the Big Bang. But the whole idea came from the fact that that light was redshifted. So again, what actually is simply happening is you're just taking that wave and you're simply stretching it if they're moving away. And if they're coming closer, you're just compressing it in a very similar fashion. So just like another similarity between sound and light where you can see a little bit of them. Right? One more, I want to talk about sound a little bit more because I know you were talking about because you said I wanted to talk about something and then I just skipped over it because I wanted to, anyways.
Yeah.
What makes, or just a little more about sound in general, right? So we were talking about like resonant frequencies, stuff like that. And I was doing a little research just on sound today. And again, I'm new to a lot of this stuff, really interested in learning more. But basically just a fundamental, but the basic thought of, hey, there are keys, right? There are certain keys that we can sing, that instruments can play and stuff like that. And the question is, if it's the same key. Now, when we say key, we're talking about frequency, right? Because we're talking about pitch. So when we're saying pitch,
Isn't that just a note?
well, yeah,
I think a key is different.
key.
Like,
Oh, is that not what I'm?
like a key is like if you play in the key of A.
Oh, no,
That's
sorry. I
different.
meant note. I apologize. I meant note. I meant like a singular note that you play is simply the question of frequency. Now, my guitar string can pluck at that frequency. A piano can also pluck at that same frequency. But they sound so different. And the basis of this sounding different is in physics called timbre. Ooh. And that is basically, I don't want to go too deep into it because me, myself, I'm not very aware of it, but I did read up on it, and it can definitely be a little hard to explain, especially on a podcast, because it does get very mathematical. But I could, anyways, that could probably be a new thing. But the basic idea is that timbre is this physical property of every single thing. Every object that has a natural frequency has some property of timbre. And that property is, it kind of revolves around various sub-properties. And those are, again, as I mentioned, I don't want to go too deep into it, but basically it categorizes into, well, how do the resonant frequencies match up with each other as you go higher? And then it also talks about the vibration patterns. That means how does each instrument vibrate? Because even though they're having the same frequency, they still have different vibration patterns. And that's actually a little term known as vibrato, which is a very common musical term that actually a lot of my friends know. But again, I'm a little unaware of that I was researching into today. So really cool stuff when it comes to simply asking the question, why does the same note on two separate instruments sound completely different? Right? Well, not completely, but you know what I mean when I say they sound different, right? So just a little bit, again, differentiating in terms of just properties that we can apply to these waves and just deducing more facts about them, right? Because they just give us more information about them and we can just deduce stuff from there. Do we want to talk
100%.
about quantum?
Yeah, we can. We can a little bit.
Talk a little bit about quantum?
There's a lot of things, especially on a podcast, where you just have to be like, just take this as a fact, because we can't really like show / explain to the extent that we would if we had like a whiteboard or if we made a YouTube video with graphics and anyways.
Yeah, whatnot, yeah.
So everything has a probability amplitude called the wave function. Everything has a wave function, which the mod squared don't even focus.
I know. It's stupid to say that.
Don't even focus on that.
I just had to, because it's not the same. But anyways,
let's say wave function. Let's think about that. God, there's so much to say.
Yeah, no, there is, but like, just talk about it. I mean, we can talk about it a little in terms of like just the wave part. Like, why is this wave function so important in terms of just waves? Like, what can it tell us about the properties of said wave that we don't get from the wave equation, for example?
Well, here's a good idea. So, God, I don't know where to start, but let's just start. Okay, so everything has a wave function, which, let's say, we live in a one-dimensional world, and this wave function is just a function of position. We don't have to focus about time. Let's say at one instance, the wave function tells you essentially how probable, let's say, this atom is to be in that position. It's just a function of x, right? And like
that is in essence what the wave function is. It tells you not directly, but when you square it, it helps you deduce a probability about a certain particle or a certain system in a certain space,
Yeah,
in
but
a certain field.
the interesting thing about the wave function is that it literally applies to every single thing
It does.
that is in our physical universe. The reason why, and I actually learned this in my lecture today. Well, there are a lot of examples, but when you study quantum mechanics, the biggest thing, if quantum mechanics was not consistent with classical mechanics, then we'd have a big problem.
Big problem.
Because quantum mechanics is supposed to encapsulate classical mechanics, right? But now, here's one thing, an example of how quantum mechanics is in fact consistent with classical mechanics. So let's say we have just an infinite well, and the way you can imagine this is that you have this interval of space that it just has zero energy, and then there's like two walls of just infinite energy, and so your particle is just bound in between these two walls, and we call that the infinite well potential.
Infinite potential well.
Infinite potential
Yeah.
well, yeah. Okay, and so there are these bound states, these allowable states, due to the nature of the wave function and the physical interpretation, which is actually very important, because if there was no tie to the physical world, then a lot of these rules that you apply to the wave function in these specific cases, you wouldn't have any reason to apply them, and then they're like it wouldn't even make sense.
I'm just saying, well, I mean, we can take this and we can then generalize it later on, which is a big advantage. I was just talking about potential wells, we didn't talk about standing waves, man.
Oh, we didn't talk
Literally
about standing waves.
It's such a fundamental. I mean, we can definitely give a little. Can we? I think that. Yeah, no. I
mean,
no.
Let's just continue a little bit.
Let's continue a little bit on the wave function. Yeah.
Okay. Where was I at? Oh yeah,
you were at infinite well.
Yes. Oh man, it would have
With
been
bound
so
states.
nice if we
Yeah,
would have spoken about.
That's what I'm
standing
saying.
waves.
That's what I'm saying.
Oh,
Standing waves
man.
is literally a fundamental part of understanding bound states. Like, why is it bound?
Yeah.
Because these are standing waves.
Yeah.
So,
anyways, okay, I'm just gonna skip to the point.
yeah.
So
Let's hear it.
the point is that these different bound states have different energy levels tied to them. Okay, and so if you imagine, like you literally have a box and you have like a bowling ball in it. That bowling ball, you would expect, right, in the classical world, that it can have any energy level, right, in terms of kinetic energy. And obviously, we'll assume that the walls of the box are infinitely strong. And so as the bowling ball is rolling across the box, it can have any kinetic energy, right? But when you look at this particle in this infinite potential well, which is, represented by this box with very strong walls, there are only certain discrete energy levels that it can occupy. What is actually interesting is that the energy level is inversely proportional to the mass of the particle. So, if you increase the mass of the particle, what happens is that the energy levels get smaller and smaller, right? Because it's inversely proportional. And the difference between the energy, like the bound states, gets so unnoticeably small that it seems to be a continuous, I'm trying to say,
a continuous,
like not discrete states, like a continuous, because the distance between the energy levels gets so small as you increase the mass, like a bowling ball, for example, you increase the mass to something.
So you just see the continuous instead of
like,
the discrete levels.
Like quantum mechanically, there are still bound states. And the bowling ball is still occupying these bound states of energy, but it's just the difference between the energy levels are so small that it just seems to be just continuously occupying any energy level that it wants to.
Yeah.
And this is not connected to waves
Yeah,
whatsoever.
I was trying to see that point. I'm like, where is the final point where it?
I just thought that was cool.
I
Was
think
that cool?
it definitely. But a fundamental thing about everything you were mentioning here, which is the point that I thought you would bring up at the end, but you just stopped, is every wave fundamentally has energy, and there's a relationship between said wave and energy.
I
Right?
just like quantum mechanics.
I know. I don't blame you for that. I mean, it's definitely one of the best.
Oh, part 3, quantum mechanics.
Quantum mechanics part 3. That might have to
No,
come.
wait, part 4. We did part
No,
3
we did
with Steinberg.
Is that part 3?
I guess.
Okay,
I
then we
mean,
can do-
kind of.
Let's see. But you lost my train of thought. What was I saying?
Standing waves.
No, I mean standing. We want to get into that.
Oh, maybe it's too late.
I mean, I just because okay, but again, a fundamental thing with the wave function is that I mean, the reason waves and wave functions are connected is because again, the wave equation is a nice way to think about what the actual wave is doing, and that's talking about the wave itself. The wave function, however, is not talking about the wave. Instead, it's talking about the object it's related to, or like a particle, like a system, a person, wave function of a person. You can have that too. Like it's just a very thin probability graph because I'm right here. But I'm saying that the wave function is very useful in simply understanding the relationship between the object and why it's waving and where it's waving. You know, it is a little different definition of a wave, obviously. Again, it's all just in the concise wave group, but it's very different. It's not a wave at all. So, when I was saying that, all waves require two fields, this is not that. This is a purely mathematical wave. So this is like another example to a wave, a non-physical wave.
I do have an idea to connect what I said to waves.
Definitely connect it, please.
Okay. So the general wave function, every single wave function can be written in this format, okay? And this actually ties to Fourier transforms. But it's an integral, because it's a superposition, essentially. If you want to create any wave, as we stated in the beginning of the podcast, if you want to create any wave, you can start with just sine waves and superpose different sine waves of different frequencies and wavelengths. And as you add them together, the shape will change and you can get some crazy looking wave.
Mm-hmm.
Well, this isn't really relevant, but all wave functions have to be normalizable. And so you could kind of imagine that it can't blow up to infinity, right? There has to be some like decrease, like asymptotal.
Asymptotic behavior. Yeah,
exactly.
It has to be. Yeah. Again, normalizable. Real quick for those probability. Again, it's a probability graph at the end of the day because you're squaring it, so it has to be equal to 1. So normalizable is just fancy term for saying integral has to be equal to 1.
Yeah. And so the general form of this wave function is, so it's an integral because you're adding these infinitesimally, whatever. You get what an integral is.
Integral. You know what an integral is by now. Come on.
So you're adding up these plane waves, which you can just, for simplicity, think of it as like sine waves. And each sine wave has a different k vector, which has to do with the wavelength. Okay.
Yeah.
It has to do with the wavelength.
Yeah.
And you multiply that plane wave by a function. It's called just g of k because it depends on the wave vector. Because obviously the wave vector is tied to the frequency of the wave, and so the g function that you multiply the plane wave by is actually the distribution of the frequencies. To be simple, it's a distribution of the frequencies. And so imagine the weight. G is like the weight.
Yeah, that makes sense. That makes sense.
And you
like
multiply, and for each value of k, which is assigned to a frequency, it gets a weight to like the amplitude.
So the heavier,
gets weighted.
the heavier,
And so if you want more long wavelength, then your g function is higher on the, know what I mean.
That makes sense.
And what you do is you integrate over a certain space of k vectors, and then you're just you're doing a continuous superposition of plane waves. And we saw this in first year, but we definitely need images for this. But as you add more and more superpositions, you can essentially get a single wave packet. If you add like two waves together, then you get some constructive, some destructive interference. The more and more waves that you add that have different like wavelengths, the more the destructive interference just eliminates like everything apart from the center.
Yeah. I know what you mean. I think I was a little okay. I totally know what you mean.
Yeah.
You're basically continuously adding them till all of them disappear.
Exactly. And so that's why it has to be an integral, because it has to be a continuous addition, so that when you're describing an actual particle, if it's a discrete sum, then there'll be some wave packet very far out.
There will.
And that's just not tied to physical reality. So the general wave function has to be a continuous sum to just eradicate those wave packets, and you're left with an actual physical description of like the position of a particle.
Damn. That was definitely a relationship between waves and wave equation and the wave function. So that was, at least we capped out our quantum mechanics talk, because that was very open ended the way we were leaving it, for sure. At least we got that. If there's anything I have to leave you guys with, is just read up on standing waves, because I feel so terrible. Because oh man.
We can try to, like, doesn't have to be a wave part 2, but it could be something where we talk about harmonics and stuff.
Yeah, maybe we can have okay, that's actually not a bad idea. We can have like a specially harmonics and oscillation episode. Like we can just
kind of the same as waves. Oscillations and
valid.
Different from waves.
No, but oscillations, we can talk about like pendulums and just different stuff like that. I don't know. We can think about that later.
Anyways.
But maybe we can add standing waves into that. But yeah, I would recommend. It's the fundamental idea is the same as a wave. It's just that it is definitely a little bit different, just the way it's defined and stuff like that. And that's also very fundamental to understanding a little bit more of that infinite potential well example that you were giving, because it's just how it's kind of done. So that was it. That was just where waves are seen. I think we kind of went over a lot of the general waves. Light and sound are the two most. I don't think there's anything other example I can think of. Two most common waves in reality, and we always want to know more about them. We found out some pretty cool facts in the 1600s. I think in this episode,
that was epic.
That was so cool, man.
100%.
Finding that must have really been something to even do that, to even attempt that. But here we are, and I think that caps it off.
Yeah,
I think that caps it off.
All right. So if you're listening to the podcast right now, go hit the follow button. Come on YouTube, come see our faces.
Yeah. And
hit the subscribe button, the like button. Make sure to leave a comment if you want to be comment of the week. We actually hit 500 followers in a week. 500 new followers on Spotify in a week.
Really?
We did that, which means that a week from now we could be at 15K. Crazy. I know. So don't forget to hit the follow button. Anything else? That's it. This has been...
Subscribe to YouTube. Go to Instagram, math.physics.podcast. If you ever want to email us any questions, any recommendations about episodes. Now you can see we're even reading comments from the email section, because some of them are really nice. So definitely hit us up there. We love your recommendations. Just last episode, we did a recommendation, and he loved it. Saw that comment, by the way. And just keep it coming. We're here for you guys. So let us know.
All right. This has been episode number 79 of the Math and Physics podcast. I'm your host, Parker.
And I'm Ray. And we will see you soon.
Bye, guys.